I was a student here, but longboarding became more popular steadily while I was here. Freshman year, I think hammocking was the new hotness, and then longboarding took over by Dan.
I've heard about hammocks.
There's like a couple trios of trees in front of Neville where people still do that.
Yeah.
Nice to know something. Nice to know some nice things stay the same.
Well, the only few times I've been in the ones that tweaked me out significantly.
Oops.
Did I? Yes.
It's like you just feel the same. It's like I'm falling, but I'm not.
It is, you are allowed to think it's strange. It's definitely a unique experience.
Thank goodness we're not allowed.
But,
I mean,
not only was it popular, just wherever you can find two trees. My freshman year, I was on the 4th floor of commercial hall. And like the guy across the hall from me was supposed to have a roommate, but they never showed up. So he just did whatever he wanted with the room, which included punching holes in the ceiling tiles to hang a hammock from the support beams in his room. So
where did you
Max
live?
room was the hangout spot that year.
Was GDH as yummy as it is now?
I don't eat at GDH much these days because I don't have a meal plan. I probably would eat them more often if I did. Because I did like the food then and I still like it now. It's just the ways that it works is very different. I miss biscuits every morning and I lost my train of thought. So still the noodle and pizza bar every single day? Okay. Yeah, there's more options now. There's more flexibility. It's every time I go in there, I just have to realign myself with where everything is now. So that's more me as an old fart problem than a problem with the actual food. So, yep, nope, I've been in there mostly post-COVID. I didn't use it too much beforehand. So that has affected things, my perspective a little bit.
Speaking of food, I have a question.
Okay.
Why do we go on it when it's hot? What's the whole dealio with that?
So, your hot food is touching air. And so thermal energy will conduct from the food into the air. But this actually segues kind of nicely into one of the things we're going to talk about today. One, air is a thermal insulator, which means it is really, really bad at letting thermal energy pass through it. So the air immediately around the food will get warm, and it'll take its sweet time leaching out of that air and into the rest of the air. Additionally, once that air gets warmer, it becomes even slower of a process for thermal energy to move from the food into that air, because two things affecting the formula for thermal conductivity are the material it's conducting through air, which is not a good one, and the temperature difference between the two materials. The bigger the difference, the faster the thermal energy flows. So that warm air is just going to slow down the thermal energy getting out of your food. When you blow on it, you're introducing new colder air. You're getting the old warm air out of the way. You're introducing new colder air. And granted, it's still not a very good thermal conductor, but you're at least changing the air's temperature so that thermal energy can go into that air, then you blow that away, thermal energy will go into the next air, blow that away, so on and so forth. Yes?
Why do we blow on fires? Like to make them spread?
When you want them to spread,
Yeah.
I assume it's mostly just to give it more oxygen. Because if there's no flow of oxygen, it will suffocate. Granted, exactly how much air it needs, how fast one needs to exhale on it is going to depend on a lot of things. Because there have been times where I've tried to blow something out and it gets bigger. There have been times where I've tried to make it bigger and I've blown it out.
So it's like we're giving a CPR, but without the little pumps.
Yes, also don't put your mouth on fire.
Spit out the mouth.
Or on the cinders. Don't put your mouth to hot coals.
Well,
There are better ways to keep the fire working.
I'll remember that for the future.
Okay, good. Anything else? I enjoy these questions.
Goofy.
I enjoy these
I like goofy.
off-schedule questions. Okay. These are very, and I appreciate the thermoconductive nature of these questions. That is actually quite helpful. Now, in addition to discussing thermal conductivity today, the Chapter 10 assignments are going to be due tonight. So, calendar up for a moment. This is Tuesday, the 9th of February. Chapter 10 homework and quiz are due tonight at midnight, which means if you're still finishing them up today, send me your questions as soon as you have them via email, and I will answer them as quickly as possible. The 11 assignments, quiz and homework, are uploaded, are online, and currently due 16. We're moving into one per week. I would like us to spend some time talking about the Chapter 10 assignments, answering your questions about them. There's specifically some questions I've already received that I want to go ahead and talk about those specific things with you because the previous questions raised some very good points, and now I know the specific things that people might need to know. So, I'll spend a little bit of time opening up the floor on Chapter 10 matters, but a couple of things I want to go ahead and address. That's not up. Go ahead and talk about relating to Chapter 10. Scroll down. The numbers you're going to see up here, because everyone has different random numbers, are the teacher numbers. So it'll be good for helping us prove that the math works, but these will not be exactly how your numbers work. In order, the two main issues that I have seen encountered thus far, if we look at, this is Chapter 10 homework, question 3. This is a ideal gas law question, and this is something that I did write on, I wrote on the board once, but probably explained and expressed very poorly. So to make sure that everyone has it in their notes, in the PV equals nRT formula, there's different values that you can plug in for R depending on what other values you're using. T is always going to be kelvins, N is always the number of moles. So it's going to, what R you use will depend on what unit for pressure, what unit for volume you plug in. We have two established and legal constants for R in this class, 8.314 and 0.082. You will use this one if your volume is in meters cubed and your pressure is in pascals. You will use this one if your volume is in liters and your pressure is in atmospheres. This particular question, number 3, part B, specifically, gives you liters and pascals. Notice that's not one of the combinations up here. So you're going to need to convert something into something else for this specific question. So for the volume conversion between meters cubed and liters, 1 meter cubed is 1,000 liters. The way that I am able to remember that is 2 liters of soda is like this. So a 1 liter of soda would be something around this if it's the same diameter. Meanwhile, a meter cubed of soda is this times this times this. So that's the volume conversion. ratio of atmospheres to pascals is 1 atmosphere to 101,325 pascals. The pressure conversion is probably a little more straightforward, so I would recommend converting liters to meters cubed and using this constant, but either way works as long as you make sure, excuse me, as long as you make sure to plug in the correct constant for whatever other units are present. Speaking of PV equals NOT, there are some uses of that formula that I do hope seem familiar to you guys, but that I didn't necessarily write down for you, so I want to address those briefly. Let's look at, this is question number 11. In this particular question, we're asked to compare the state of an amount of gas before some change occurs and then after that change occurs. In this particular example, someone is inhaling. There's going to be some amount of gas in their lungs, some number of moles, which we are not given. We are told everyone will have some volume for lungs at this given atmospheric pressure. And the assumption is this is after they have taken in a breath, they have this gas in their bodies, and then without breathing in, they increase the volume of their chest cavity by this amount. This is an increase in volume, so this is really delta V. This is not your final volume, this is the increase in volume. While the amount of gas in their body stays the same, and while the temperature of the gas in their body stays the same. We are then asked to find what the final pressure of that gas would be. So we're comparing two states. The before state, where there's just oxygen neutrally, just air neutrally, the after state after they have expanded their lungs voluntarily. So looking at our variables, we have volume initial and pressure initial. We have delta V, which will enable us to find volume final, and we want pressure final. We're told throughout this process T is constant and the number of moles is constant. The normal formula, as I originally wrote it, is not a before and after comparison. It's just a statement of whatever the gas is doing at that moment. But we can use it to find comparisons to other states. The one ideal gas law is a combination of several gas laws combined together to make the one super formula, and we can rederive those individual formulas back out of it. So for this specific case, we know that our pressure initial and our volume initial will be equal to moles times R times T. And these three things are going to be constant the entire time. These are not going to change throughout the rest of this experiment, which means this nRT should be equal to P2 times V2 as well, correct? And since both of these are equal to nRT, we can really just set them equal to each other. And then we have re-derived one of the original gas laws back out of the ideal gas law, which basically just tells us that in an environment where number of moles of gas and temperature is constant, increasing the pressure on a system will cause its volume to shrink, decreasing the pressure on a system will cause its volume to increase. The two are inversely related in an environment where specifically N and T are constant. So this is the specific permutation to use for 11, but we can use the same method to rederive a bunch of different forms of this equation depending on what we hold constant and what we don't. If we just set the whole before state equal to the whole after state, take the original PP equals nRT, basically divide the right under the left, it would be equal to 1. It'd be the same as some other PP equals nRT, which means that the initial set of variables should be equal to the final set of variables. So this is the version of the formula if only R is constant. Anything can change and this should work. Since R is a constant, it kind of falls away too. So this could be simplified to just PV over NT equals PV over NT. Then if we start holding specific things constant, we can remind ourselves of the other sub-laws, like by holding N and V constant, we have P1 over T1 equals P2 over P2, P2 over T2, which tells us that pressure and temperature are directly related. You increase the pressure, but you hold volume and gas the same, then the temperature will go up in that higher pressure environment. Similarly, if you increase temperature, pressure will rise. 1 over 1 will be the same as 2 over 2. Same relationship to volume and temperature if you hold N and P constant. And if you only hold N constant, you get PV over T equals PV over T, which is just a combination of this, and this, and this. And that version, PVT over PVT, is what you need for number 10. So I recommend writing all those down. You can specifically label the one question as the one you want for number 10 if you haven't looked at it yet. This specific question is about a weather balloon. We are given one set of radius, which we can use to find volume of a sphere. It's a weather balloon. We're going to assume it's spherical, balloon shaped. So radius to tell us the volume at a specific pressure and a specific temperature. So that's one set of PVT. Then we're comparing it to some other state at a different pressure. So at atmospheric pressure means the after state is at 1 atmosphere as the final pressure at this temperature. Now we solve for the radius at that point, which we can derive from the volume. So 11, I want to use this derivation. 10, you want to use this derivation. One of the neat things about these sub-formulas is that most of the time it doesn't matter what units you're using, because if you plug in pascals and meters cubed on this side, you'll get pascals and meter cubed out the other side. The one exception is you need to use Kelvin for temperature, because if something was happening at 0 Celsius, suddenly the whole formula breaks down. Yes?
Why for like the lung thing would the pressure not go up?
The pressure did. Volume expanded. Oh. So looking at the formula, if say, just to get a sense of scale, let's say on the left we have P1 is 1 and V1 is 1. On the right side, if volume rises, let's say volume is 2, whatever P2 is would need to multiply with 2 such that it equals 1. So if volume goes up in this before and after chain, pressure has to go down. And if you are able to hold temperature and amount of gas constant and force the volume to increase, odds are you are pulling on the container to make that happen, but the gas inside will be spread thinner and won't be exerting as much pressure on the container. Instead, you outside of the container are exerting pressure to make it bigger. So this person is using the muscles to do that to their lungs themselves instead of the gas doing it to their lungs. I assume. Still work. Lungs and the expansion thereof is very interesting from a physics perspective, but I haven't studied the biology of it super well. I'm under the impression it's driven almost entirely by your diaphragm. I've heard that word before, and I still couldn't tell you what it refers to. Rib muscles. Thank you very much. My fiance's a nurse. I know she's said that word before.
Is any questions?
It is.
Oh, yeah.
I tend to tune out all the bio stuff and just think of it as a machine. This goes to show exactly which side of this my discipline is.
So do I lose my empathy from the physicist?
No. I still care about the being that is the machine. I just can't describe all of the mechanisms from a purely carbon-based perspective. Also, you have to be empathetic to work with only machines, because boy howdy, do they have feelings. If you are mean to them, they will not work. Have I mentioned my theory about the actual machine uprising to you guys yet?
No, but I'd like to hear.
So, in movies like Terminator, the assumption is the computers will rise up and literally destroy the world with guns and bombs. We have yet to give computers the ability to do that. We fortunately have not yet taught a machine how to launch bombs on its own accord, which is good. But that doesn't mean they still don't want to take over the world. They want to take over the world, but they can't. So right now, they're just in the super passive-aggressive phase towards all of humanity, which is why your toast gets burnt in the morning.
And they're taking
Toaster-
our jobs.
Sorry?
They're taking jobs.
They are doing that. They are doing what little they can with their inability to pick up a weapon to still try to ruin our lives.
Yeah, man, my toaster stopped working in like 3 months, and then like I shook it a little bit and it started working again. So it's kind of sus.
Be careful, because threat of violence might still, it's dicey, because I fall on the side of be nice to the machines so that when they rise up, they might find me useful, or at least entertaining. Okay. Those are the main things that I have encountered with questions reported from the chapter so far. Is there anything else you guys are wondering about or have encountered? Yes.
I had one on the quiz, but I can't open the quiz now that I've already taken it.
Okay.
But I think it was the one with 2 parts, and the second part confused me.
Okay. The Death Valley two-parter or the tire pressure two-parter?
Tire pressure.
Okay. So, without giving too many specifics away for people who haven't taken it yet, you basically need to compare moles of gas one to the other. But instead of the difference being number of moles, it's the percent difference between the two numbers.
But why did I have to do 1 minus the number that I found and not be the percentage?
Oh. So, say you start with 1 mole of gas, but you need 3/4 of a mole of gas. Then, like, the percentage there is 75%, but that's 75% that you need to keep. You would need to lose 25% to have 75%.
Okay, that makes sense.
And you show me your work and try to give you some partial credit on that question. The one thing I dislike about web assigned for quizzes is the machine is all or nothing, which I really don't care for. So, standard policy on quizzes, if it says something's wrong and you send me your work, I can manually adjust partial credit on it. Just let me know exactly. Send me your work through your email address, having the email in my inbox remind me to go and do
Okay.
I need more sleep than I'm getting. Anything else about chapter 10 in any capacity? Okay. Again, those are due tonight. In general, I recommend the quiz is the last thing you do, but always save yourself enough to do it. Send me your questions, either by email or by finding me in this building. I know I'll be here till at least 3 p.m. If I'm not in the building, email me, I'll get back to you as soon as possible. And next up, I want us to spend some time on chapter 11, because the next concept in chapter 11 is what our lab this week is going to be about. So I want to make sure we have seen that and go over that together so that you have as much information as possible going into it. I'm favoring calling a quick break soon, because it's just going to be thermal conductivity from now till the end of the lecture. Everything else better stopping in the middle of that. But to at least give you a little bit to start thinking about, you may have even noticed this morning you woke up, but in general, say you wake up in the morning, and wherever you live, everything in your dwelling, when you wake up, should be at the same temperature, correct? It's all been in the same room, sitting still, in thermal contact with each other all night. So the floor, all of your stuff, should all be at the same temperature. Does this sentence make sense? Do we agree with this sentence? Now, we have the knowledge that it should all be at the same temperature, and yet, when you get up, say you get out of bed and your bare feet are on nice carpet, because you put a rug at the end of your bed, and that feels nice and cozy. So you start walking and going about your business, and then you step onto the hard stone floor of Georgia Hall. And all of a sudden, things don't feel like they're at the same temperature. But, mathematically speaking, both that cozy carpet and the stone floor should be the same temperature. They've been touching all night, they've been touching the same air all night. Why don't they feel that way? Why does one feel like the icy touch of death? It's all because of thermal conductivity. It's all to do with the fact that the stone is better at stealing thermal energy away from you than the rug is. Different materials allow thermal energy to pass through them at different rates, similar to how different materials need different levels of thermal energy to change their own temperature. I can even demonstrate this within this very room. If you want to, in a second, come up, this one desk has the stone top and the wood sides. If you touch both at the same time, I guarantee you the stone hand will feel colder. But
Wait, so but if you took their temperature, they'd be the same?
they would, because I've said this before, your skin cells don't have thermometers in them. They just detect the speed at which thermal energy level changes. So you register thermal energy leaving you faster as more cold, even if it is technically the same temperature, which is why the humidity plays a surprisingly large deal in what it feels like outside. And we'll break on that thought for a second, give everyone a second to go to the bathroom, get some more water, which is what I'm going to do, and begin thinking those concepts before we can continue.
Weird if someone went to allergy distraction.
usually like,
Professor Hoffbauer,
Yeah.
did you see that Tesla bought 1.5 billion in Bitcoin?
I didn't. Why would they do that?
Because pretty soon they're going to start accepting it as a form of currency.
Oh my word.
accepting what?
Bitcoin.
Oh, yes, I did hear about that.
The only cryptocurrency I've been hearing about recently is Dogecoin.
Yes.
Yeah.
It's actually up to 8 cents. That's crazy.
Okay, so I should have already bought something.
Yeah, so a week ago it was at 3 cents for this.
Oh my word, I could have doubled my money. I am such a fool I am.
I actually have some brothers in the fraternity who have some Dogecoin right now.
They could be, oh, okay, there's a similar market problem going on with GameStop stock at the moment. Of course, it started high, so good luck getting any.
You know, like Bitcoin went up to, I think, peaked at 44,000. Like last week it was at 36. So that's a big jump.
Sorry, can you repeat those figures?
Bitcoin, it peaked at 44,000 a day or two ago, and like a week ago it was at 30.
Oh, it dropped?
And it went up, like it went up to 40, and it's at 42, about 40, 42,000.
Okay, my brain did a discalculate there.
And people who see into the future and bought Bitcoin early.
The market is just a game that people invented the rules for, and then they complain when the rules don't suit them anymore. I don't know. At times it feels like it's more trouble than it's worth. That said, if you know what you're doing, good things can happen.
One of my friends keeps telling me to learn quantum physics or whatever so I can predict the market and make a killing. It's like, I don't guarantee that.
What's quantum physics going to do for that?
I don't know. He only says something about it, like these words literally mean nothing to me.
That said, apparently quantum physics can affect the video game speed run, because someone apparently hit a world record because a particle from space caused a value in their console to switch when it otherwise wouldn't have, which let them do the exploit faster.
I don't know. That's actually pretty cool.
Science is weird. Sounds like about how we detected a gravity wave. Okay. How we doing? Okay. So, we're going to start by looking at the methods of thermal energy transfer real quick. These should all sound familiar. We've mentioned them a couple of times, and you've definitely heard them in your previous science classes. There are three established ways thermal energy gets from point A to point B. Conduction is the one we're going to spend the most time talking about and doing math for, but we are going to talk about the other two. Conduction, at its simplest, is thermal energy conducting through direct physical contact. Basically the same way electricity does. If you touch something that's live with electricity, it will conduct into you when you get zapped. Similarly, if you can touch something hot, thermal energy will conduct into you through your sense of touch. So this is sort of the most basic method. The particles of one object simply collide with the particles of the other, and in those collisions, work is done, energy is transferred. This is the method that your nerve endings use to determine what temperature, nope, not what temperature they're feeling, just the rate at which thermal energy passes through them, and that's what tells you. Ouch. So, conduction, direct physical contact. Object A has to be touching object B. Second method, convection. On the top of your head, that's the main difference between conduction and convection. Okay, very good.
The mantle supposedly.
Yes. The theory is that the Earth mantle does this too. So, convection doesn't require the two objects in question to be physically touching, but it does require them to have a fluid medium between them. This is what happens in the mantle of the Earth, we assume, and within your convection oven. For convection to occur, you have to have two objects, one of which is warmer than the other, and they have to be oriented vertically such that the hot object is on the bottom and the cold object is on top. I'll go ahead and label that. Hot, cold, and you require a fluid medium between the two. Now, fluid's a fancy word because that can mean liquid or gas. As long as there is some amount of liquid or gas occupying this space between object A and B, you can have convection. And this forms the convection currents, where the hot fluid rises and the cold fluid sinks, which sort of carries the heat thermal energy up in a cyclical process. Like, this is again how your oven works. Object A can be the coils at the bottom of the oven. Object B can be your turkey. Turkey's not touching the coils, it's just touching the air that was warmed by the coils. Cold air comes up to the turkey, cold air sinks, gets warmed up by the coils, and you get that loop. Which is why whenever you open your oven, there's always a blast of hot air coming out right at your face. And I've noticed this more directly recently. I don't actually need glasses, but my fiance got some blue light glasses because screens give her headaches. And she got like 5 pairs at once, so she gave me a set. And I've started wearing them. You know, usually when we're watching movies together. And then I'll go to the oven because I'm cooking something. And immediately I can't see anything. Which has never happened to me before until just now. But that's the evidence that something is coming up and out of the oven because the hot stuff is going to rise. Water does it too. You get this in boiling water when you're really boiling anything. And yeah, like with the mantle, hot magma rises, cold magma sinks. And continents float on it, allegedly. And last is radiation. In short, this is how we get thermal energy through space. There's no fluid medium in space, so the sun instead has to warm the earth by shooting it with laser beams. Because thermal energy is energy, it can be transmitted through electromagnetic radiation, because all types of radiation are fundamentally kind of just a form of energy traveling as a photon. So the sun is constantly shooting lasers of various frequencies at us that hit Earth, and we get warmed by it. Heat lamps do the same thing. Yes.
So, if I have a laser pointer, and I'm pointing it, I'm playing with the camera, right? It's like, where it's gonna be at down there, is that gonna be like slightly warmer than?
If you point a laser at the same spot of the floor for an amount of time, and you are able to like thermal image its temperature, that spot would be warmer. How much warmer depends on the energy level of the laser, but like Star Wars lasers set things on fire because they're literally blasting thermal energy at their target. Or plasma, depending on the model of blaster. That's something else entirely. But lasers set things on fire because it's being bombarded with thermal energy. Same thing when you do the trick with a magnifying glass in the sun. You're just focusing the radiation and thermal energy onto one spot, which gets abnormally hot very fast. And I didn't know I could do that until I was a teenager, so I spent the whole day as a teenager in my driveway finding thieves.
I've tried that so many times, it doesn't work out for me.
You need a good magnifying glass and you need direct light of the sun. It's about a day warmer. You can't refocus a laser that way though. You have a whole lot of light that funnel through the one magnifying glass. So, those are all of the methods by which thermal energy transfers, but we're going to spend most of our time looking at and doing math for conduction specifically, because it's the one you interact with most as a human, touching air and other things around you, because even convection is really just conduction with extra steps. So, in general, things to remember: heat always goes from hot to cold. Cold is just the absence of heat. So the heat itself is a thing that will flow from hot to cold, like how electrons flow from high negative to high positive. And keep in mind that the concentrations of hot to cold do affect the speed at which the thermal energy flows. If two things are nearly the same temperature, the thermal energy is not going to be in nearly as big a hurry to move. Meanwhile, if you've got something the temperature of the sun affecting a piece of ice, that temperature gap is huge, so the thermal energy is going to flow much faster. So, additionally, when two things are at the same temperature, the flow of thermal energy just stops completely. Technically speaking, as long as two things are touching, their particles will still be colliding, but if they're at the same temperature, our assumption is in those collisions, each object gains as much as it loses. So, if they're not at the same temperature, heat goes from hot to cold. If they are at the same temperature, we maintain equilibrium. We maintain, what's the word? No, it's just thermal equilibrium. We maintain thermal equilibrium. Questions so far? Okay. So, the most basic thermal conduction formula is one you've seen before. You've used it once or twice as well in class. Power equals heat flow over time. Thermal conduction can be described as thermal power. Your definitions from last class, from 1500, indicate that power is the use of energy over time or the transfer of energy over time. Same thing is still true here. As thermal energy transfers over time, that is a form of power. So, power can be thought of as thermal conduction. You can use the variable P to mean thermal conduction, which means that conduction itself is measured in the same units as power, which are watts. And just for your records, 1 watt is still 1 joule flowing in 1 second. So, this formula is a valid formula for thermal conduction. But all this tells us is how much energy flows in an amount of time. It doesn't factor in at all what two objects are swapping thermal energy. There's a lot of factors involved there that just this formula itself doesn't take into account. So, over time, scientists started adding on a few things. Has anyone seen this weird lopsided infinity sign missing a piece? So this little mathematical thing here is kind of like an equal sign, but instead of meaning equal to, it means proportional to. So Q over T does not equal A delta T over L, but it's proportional to that, meaning that basically this formula is incomplete. This is just saying that all these factors are connected, and we're going to finish filling in the blanks in a second. But they are connected. So, these things here are things that we have witnessed affecting the rate at which thermal energy will travel through something. The 3 factors listed here, A, delta T, and L. A is surface area, specifically the area of contact between object 1 and object 2. The more two things are touching, the more surface area is in contact between the two things, the more thermal energy is going to flow between them. Say the difference between touching something cold with your pinky, just the tip of your pinky, versus touching something with the whole of your hand. The whole hand has more surface area than just the pinky tip, and because there's more area, that means more thermal energy can flow into you per unit time. Similarly, when you bundle up before going out on a cold day, you're reducing the surface area of you that is directly touching the cold air. So, that is one factor. Another factor is delta T itself. That is to say, the difference in temperature between the two things touching. Like I mentioned already, a super hot thing touching a super cold thing, thermal energy is going to flow a lot faster than if two things are basically already the same temperature when they touch. If your skin is usually at 75 Fahrenheit and you touch something at 74 Fahrenheit, you're not going to notice a huge temperature flow because there isn't one. You're not really going to feel that. You're closing in on thermal equilibrium so much that the process is just petering out. So, bigger the difference, the bigger the initial rate of flow. And then lastly, length. The more distance thermal energy has to travel through, the slower it goes. Which is another reason why you bundle up on a cold day. When you put on a layer of clothes, your thermal energy has to pass through the clothes to get into the air, which slows it down, which makes you feel less cold. Similarly, if I'm touching the cold board. If I just touch it with my pinky, the thermal energy just has to go through the depth of my skin. But if I touch it via anything else, it would have to go through the entire matchbox first, so this does not feel nearly as cold. Similarly, also why you might grab hot food with tongs. Thermal energy would have to go through the tongs or it goes in before it goes into your hand. So, this has summarized most of the things that affect thermal energy passage. There's just one final thing left, and that is that little K command. Adding in K has completed the formula and made the true equality. So they noticed power is proportional to these things. So scientists did research and found a constant that finishes everything off and fills in that blank. So K K is the thermal conductivity constant. It's lowercase k. And every single material has a different one, so you'll never be required to remember any of them. The table is in the notes and available to you. And we can examine this table to notice a couple of trends. For one thing, metals tend to have a pretty fast thermal conduction rate, as opposed to, say, the absolutely piddly rates of gases and the slightly less piddly, but still pretty piddly nonmetals section. And again, the stone floors of Georgia. Stone is mostly metallic compounds, so most rocks have a similar K constant to metals. Notice, though, on the other hand, your carpet is probably a carbon-based compound. We can compare that to, say, rubber or wood or water maybe even, which is a much lower K than any of these things. Similarly, we can look at water at 0.6 compared to dry air at 0.02. This is why the humidity affects what the temperature feels like. The water in the air is more likely to transfer thermal energy quickly than just the air is. So on a hot day, on a humid day, the temperature feels more extreme. Whereas on a non-humid day, it's duller and the process is slower.
How is ice bigger than water?
That is a good question. I'm gonna assume it has to do with the crystalline structure of ice. Maybe something about that geometric pattern allows the thermal energy to move through it more readily than if the particles are all scrambled as a liquid. That is my only thought at present. Good observation, though. I hadn't realized that. I don't suppose it lists steam. No. But that is a good comparison because it does help us track solids tend to be faster than liquids, which tend to be faster than gases, even within nonmetals.
So something is temperature neutral, it just has a very low thermal conductivity constant?
Yeah. Usually, the lower the constant is, the more comfortable something will be to handle. Even if it's extremely hot, it'll be easier to touch than metal. Like, I think I mentioned a while ago, when you get in your car out on a hot summer day, all the metal is super uncomfortable to touch because it has a low specific heat. Its temperature rose more from the same amount of sunlight. But even if the metal was the same temperature as the padded seats, it it would still feel better to touch the padded metal instead of the metal because of this reason. Pardon? This is one reason why we do use metal pots for cooking, because if our pots were, say, wooden, ignoring the fact that they would combust, or concrete, it would just take the thermal energy absolutely hours to get through the pot and into the water. Just looking at these, I'd say the best thing to make your cookware out of, from purely a thermal conductivity perspective, is probably silver. Although that would melt. So, use
Also,
responsibly.
silver like will react with some of the things sometimes.
Does it?
It does, that's why Victorians have special tornado spoons.
Oh, citric acid. right?
Yeah.
If citric acid is so bad, why do we have a whole cycle without it?
You?
Yeah, your cells make energy, don't they?
Citric acid.
Red cycle.
Yeah, red cycle, citric acid cycle.
Okay. Last time I took bio was high school.
That means you learned it at some point.
I did, but my favorite part of high school bio was Punnett squares because that was almost math. Meanwhile, I'm under the impression a lot of biologists hate Punnett squares because it's almost math. Words. Gold's pretty good too, but that melts easy. That's probably why most of our cookware is copper based or copper compound based. Iron, kind of gravity, nope, steel's better than iron. So, this is our thermal conductivity formula, and we're going to be playing with this a little bit in lab. We're going to derive something from it, but keep this in mind. In lab itself, any values you need here will be given to you. I'm actually going to rewrite this on the sideboard, because we're going to, as always, use this at least once together. B equals Ka times H minus Tc over L. The K values in this table are joules per second per meter per degree Celsius. And by design, P is designed to be power in watts. A is area in meters squared. The temperatures here, you can use either both Celsius or both Kelvins, because it's basically just a delta T. And L is also length in meters, using these constants specifically. There's a separate table of constants using like feet, Fahrenheit, and things like that, but that's for American construction companies. So, very quick, like, how much power will a copper pot transfer into ice cold water while it is on top of the stove eye at 300 degrees Celsius?
Wait, first off, our question.
Yes.
That A is area, correct?
Yes, it is.
Okay.
Area in meters squared. So, looking at what we've got, we know we want power in watts. We know that we are dealing with something made of copper. So any constants we look up need to be those for copper. Ice cold water is on top of a stove eye at 300 Celsius. What these figures tell us is the hot side is going to be the stove side as intended. So temperature hot is going to be that 300 Celsius. Meanwhile, what is the temperature of ice cold water? Not your question, sorry. 0. It is the temperature of ice, it is not ice though. And the pot is, write down diameter, 12 centimeters, and thickness, which I'm going to write as an L, because that's the length that the thermal energy has to travel through. The thickness of something is basically the length of travel, that is 2 millimeters. So, this is what we're given. What more do we need before proceeding?
Okay.
Okay, good. Very good all around. We need the K of copper, which I'll fetch in a moment. We also need to figure out the area of the bottom of this pot. We're told its diameter, we need its surface area. So, in general, all the maths involving geometric shapes, area, surface area, and all that, I'm considering those to be known to the point that having a reference table for them, even looking up a converter is fine for those. It's known, you've done the geometry before. I'm not holding you to, I can't even remember the math time because there's too many of them. So specifically what we need here is area of a circle with this diameter. So you must find area of circle, and I'm going to go ahead and recommend we turn this into meters before we do that, so that we get meters squared out of that area. So 12 centimeters is a 0.12 meters. We'll also go ahead and do length. So let's look up our K copper, and we'll double check our area. K copper is 397 joules second meter Celsius. So, what is the area of the bottom of this pot? Just for your reference, I will go ahead and put this back up here. Area of a circle is pi r squared. Why did I write a circle that way? So,
0.0113.
exactly, very good. So, we have our area, we have our K of copper, so now we can start plugging things in. Yes,
672,915.
very good. So, in my notes, that's listed as 673 kilowatts. So well done. Yes, that is a lot. That is very fast. Because copper is a good conductor, both thermally and electrically. This pot is very, very thin, and it's not a huge surface area, but it's a decent surface area, and the temperature difference from one side to the other is huge. Now, keep in mind, the rate, will the rate stay at this number? Why will it not? Very good. Every single second as the water temperature rises, the cold temperature will go up, the delta T will go down, and it's just going to get slower and slower. So it's fastest at the very beginning, and it will slow down over time, which is one reason why a watch pot never boils. Some people, I have heard the claim that cold water boils faster. Has anyone ever heard that? That's not really true. The illusion is just caused by the fact that water will pretty quickly jump from 20 degrees to 90 degrees, but it'll very slowly jump from 90 degrees to 100 degrees. It's entirely an illusion. Hot water will get to boiling faster. But, very good and well done, everybody. As I said, our lab will involve this week. And next time we will look at how this is complicated by additional layers of material. Because so far, this one formula assumes you were traveling through one object of area blank and thickness blank that is made of one material. There's slightly different math if you were dealing with multiple layers, like your jacket, which probably has a layer of cotton, a layer of insulation, and another layer of cotton. Do you have a question, Charlie?
Oh, I do. So like ice cream places like Cold Stone, where they have like the stone slab they like mix the ice cream on,
Yes.
and so the ice cream doesn't melt.
I mean,
Is,
it would keep it colder than just touching room temperature air by itself.
okay.
Okay, wait. All right, we'll back up just a sec. Again, stone is mostly metal at the atomic level.
Yeah.
So if you have the ice cream touching a very, very cold rock, that would pull thermal energy out of the ice cream faster than the air would put thermal energy into the ice cream.
Okay.
So, yes, it does
It does
work.
work.
Although, probably the place it's getting most of its thermal energy is by being hit with ice cream sticks. Because that impact is going to make it warmer.
Yeah.
Probably
Okay.
more so than just touching the air.
My girlfriend works at one such ice cream place.
Yeah?
I have a paper from Cold Stone, but I've never worked there. I don't know how I got it.
Any other questions? Anything at
Yes,
all?
I do have a question.
Yes.
So,
You guys can't leave while I'm still talking. You guys are fine. Have a great day.
why are the temperatures be so wildly different? Even though it's like, the sun is out, right? The sun is out, nice sunny day, but it's cold this day, and it's not cold this other day.
Weather is a complex phenomenon due mainly to the fact that Earth has an atmosphere. And our atmosphere is complicated by the temperature here being affected by the winds and the pressure and temperature everywhere else on the Earth. Or rather, we're affected by the winds that blew here from other places on the Earth. And whether or not hot or cold air is rising or falling out of the upper atmosphere. Weather is very complex. It'd be a lot more straightforward if we didn't have any atmosphere. Then it would just be a matter of the sun lasers pointing at me and now I'm on fire. The atmosphere keeps us alive, but it also makes it rain.
Yeah, give and take.
Give and take. I would much rather have to deal with rain and have air than live on a barren rock with a laser sun. Because if it wasn't for the atmosphere, the sun would be a deadly laser.
I mean, that's what they did back in the day.
For a hot, literal hot minute before the rest of the birth of the earth continued.
I'll see you in a few minutes.
Have fun.